Hi, everyone. I'm Nima. I'm the AVS research lead at EigenLabs, where we work with a variety of projects building on top of the EigenLayer protocol. We have here with us Payao, who's the head of research at Witness Chain. She will be walking us through what Witness Chain is doing as a DePIN platform and their first project, a watchtower network, and how that's designed, the use cases, the motivations, etc. So without further ado, yeah, please.
Thanks, Nima, for the introduction. Hello, everyone. So today I'm going to introduce the technical framework of Witness Chain and demonstrate how to interact with our system. And I will start with some high-level overview of the system design of our DePIN coordination layer, or in short, DCL, and then work through some smart contract interfaces and also explore specific use case of the watchtower network. So to just give you a bit more context, Witness Chain aims to unify the DePIN economy by creating a platform where diverse DePINs converge to create shared values. And we know physical infrastructures are a natural fit for decentralization, but they've been taken over by those monopolistic companies due to the high capital requirements. But today, thanks to our community and the blockchain platform, more and more DePINs are awakening to their decentralized nature. But due to the variety of those physical assets and the complexity of dealing with them, one key challenge we identify is to coordinate different parties. And the coordination is crucial not only among those DePINs themselves, but also with other applications in the digital world. So at the core of our solution is building physical trust by establishing consensus on physical states. As you know, people trust Bitcoin or Ethereum because they establish the consensus over the balances, some these digital states. So similarly, for DePINs, it's necessary to establish consensus on the physical states. And we have developed a series of protocols that can reliably verify those physical attributes, such as location, bandwidth, and competition. So this protocol represents some research breakthrough in this respective field. And together, they serve as the building blocks for developing a DePIN application that require physical trust. So, and these trusts are will be anchored by the economic trust supported by EigenLayer. So I'm going to share the screen here for the structure of our DePIN coordination layer. Yeah, so here's the main architecture of our DePIN coordination layer. So on the right-hand side, we have categorized 4 classes of entities involved in the system. They could be DePIN chains, which are the provider layer where physical infrastructure resides and the state information originates. We have over 20 DePIN partners, and many AVSs also sit in this layer. They can use the proofs as needed, for example, to incentivize their geo-decentralization of their own operators, or to set up some regional constraints based on their applications needs. And we also have, so people can join the system as an application builder. This includes the developers, users, investors, because they can build DePIN dApps and participate in the financial protocols around these physical assets once they have consensus on the states of these assets. And so as we mentioned, the core of the system is the proof, the set of proofs. So people can also join the system as a proof system contributors. And our system supports a pluggable proof of X. That means, besides the protocols we already built, we also allow our community to innovate and extend their validation processes tailored to maybe their specific physical assets. So in terms of this layer, there are a very diverse ground for the integration and collaboration. I'll give you some examples. Like one of our partners, Andrina, they're providing the network infrastructure. They're working with us on a new implementation of our proof of backhaul protocol with the DPDK framework. as a strategic solution to verify high bandwidth capability in their specific hardware nodes, because so they can like implement full backhaul protocol, then bypass they can fetch the traffic directly through the network instead of like to bypass the OS processing time. And some other example for the Daylight, which is also our partner on the energy infrastructure side, they propose their own protocol to verify the flexibility of adjusting the energy devices. Because the energy devices, they may have different types of capacity, and we need to verify. They will also like use the proof of location to first make sure the energy device is in the same building of the monitor of the other device. And then after that, they can use their monitor to further send the data, and the challengers can help verifying the capacity and whether they can just change the states as you request. And so behind this progress, what we want to do is to set the new standards for how the physical trust is built and maintained. And at the bottom layer, we also have all these operators from EigenLayer mainly, and also other community partners. They are the entities that actually running the challenger client software, and they will, for example, register on EigenLayer first as operators and allow those risk takers who delegate to them. And they are the entities that take the responsibility of providing economic security and monitoring activities in those challenges. And our partners can also participate in this layer. For example, GeoNet, they have a bunch of operators like to run our proof of location protocol to provide a very high accurate estimate of the location. So at this stage, our proof of diligence protocol is already live on mainnet together with EigenLayer's mainnet launch. And these protocols are mainly running by those watchtowers, the operators, for monitoring the roll-up states. And for proof of location and bandwidth, we have a version under testing, and we also expected to launch them in the next couple of months on the mainnet. And before diving into the details of like each proof, I will first discuss our general interfaces provided for different participants to access the system. So here, this diagram depicts the architecture of our DePIN coordination layer smart contract and some of the off-chain components and off-chain interface. So the smart contract side features three main modules. The first is the challenger coordinator contracts. This is designed like for each proof, you need to provide a standardized way to first create the proof specification and also coordinate the proof generation and the challenge process. And also you need to specify how we can verify the proof on chain. It can be as simple as the signal track or like include any other complex rules on the chain. And besides contract, each proof also need to develop an off-chain part, including the prover and challenger client to measure the corresponding physical state. For example, for the proof of location or bandwidth, you may implement the challenger client to send the internet measurement packets and the response, this kind of logic. And the second category is the registry contract to maintain the on-chain identities of different parties involved in any proof. This can include the provers, challengers, stakers, and even those tokenized assets and the different DePIN chains. So basically any like parties you want to have an identity on chain when participating in the proof to earn incentives or to build your reputation, you need to first register to participate. And the third category are the basic interface contracts. And at this point, we provide a request handler contract as the entry point of all applications to use any proof of X. So the request can contain a sequence of sub-requests for different states. If you want to query the location and bandwidth of some of the same prover at the same time, you can just combine them in the same request. So this will facilitate the composability of proofs. You can simply issue a sequence of requests, or you can further implement your logic to combine the proofs to further calculate a composed proof to implement a more complex logic. And so this is the basic architecture of our contract side and how the application can use it, where to send the request to, and what is SDK we will provide for different off-chain parts to run. And then I will go through some details of the 3 protocols we already deployed: the proof diligence, location, and bandwidth. So I will go to our website here. So we have some introduction and explanation on our website for different parts of the proofs. And the rollup watchtower implementing the proof of diligence protocols is currently live. And look at this this diagram. So just as a background, why we are going to design this proof of diligence protocol, because as a key component of the burgeoning layer 2 economy, the rollups are currently very essential for enhancing the scalability of those blockchains. So the key idea, key idea behind the optimistic rollup is to conduct all the computations off-chain with only the proof and the updated state maintained on-chain. So this system will remain secure unless some fraud dispute arises from the application layer, and at which point it can be resolved by a set of defensive validators in their rollup protocols through some on-chain mechanism, such as interactive verification games. However, there's a well-known vulnerability remains despite the security layer already provided by those defensive validators, because there's no inherent guarantee that these applications will consistently monitor the asserted states. And this critical question then becomes how to ensure the diligence in this normal path when there's no faults. And in other words, who is watching the watchers? So our protocol is designed to solve this problem. We introduced the concept of these watchtowers. They backed by the stakes and the economy security, and they need to run this proof of diligence protocol. The main idea is watchtowers, they're incentivized to constantly monitor the transactions during the normal path of operation. And they will operate independently and only interact with the existing rollup system if they detect some incorrect state. And to ensure they fulfill their watching responsibility all the time, they must provide this proof of diligence for earning the incentives. And meanwhile, other watchtowers also need to watch the process of this proof of diligence and verify the proofs accordingly. So to go through the diagram here, we have some witness chain. Here, the incentives, we call the bounties, and we will first initiate some bounties for each layer 2 chain for monitoring. And then the bounty miners, those watchtowers, they will register first. And then upon receiving some event from the layer 2 contract, those clients will start validating the states by tracing the transactions on the layer 2 archive node, where they will also run an opt-in for the proposed block. And if they find the state, after recomputing the state, they find they're consistent, they also need to see whether they are self-selected as the bounty winner. If it is the case, they will go and submit this proof of diligence, which is some hash commitment computed from their own transaction trace route. And after that, on the other hand, if they find something like any inconsistent state happens, the watchtower will submit an alert to this alert manager contract in addition to provide a proof of diligence. And on the top, we have an aggregator, which currently is a centralized entity to aggregate the proofs by listening on the events of those diligent proof manager contract, and it will compute the winning watchtowers and submit the winner details to the settlement contract, and further the rewards will be distributed based on the current execution. So these roll-up watchtowers are currently the major application of proof of diligence protocol. And at the end, I will also go over a very specific application of it, which is a transaction chaser API we built for to implement anything like L2 bridges, where you can just be a light client. And beyond these roll-up applications, we are also exploring the additional opportunities to use the proof of diligence. So for example, we recently released a paper jointly with EigenLayer and Princeton University proposing an unconditionally safe light client protocol for Ethereum. So the protocol is developed on top of this proof of diligence protocol to provide a monitoring servers for the proof of stake light clients.
Hey, just a quick note before we move on. Can you elaborate on what happens at step 5 when we interact with the alert manager contract? What does the contract do next?
Which one? The
number 5, when we interact with alert manager contract at the bottom.
Yeah.
So what does the contract like? What does it take as input? What does it do with output? Yeah.
Yeah. So this alert contract is also the only connecting point to the existing rollup system, because they also the existing rollup scheme also relies on those flow proofs to actually like detect when the asserted state is wrong. So at this point, they will on the one side, for our protocol, there will also be some like slashing. It will further connect to the EigenLayer slashing mechanism, because if they detect the state asserter like send something wrong, they can further resolve this dispute on chain and like determine which one is incorrect, which one is correct. And further, they can also connect to the rollup side to inform their defensive validator. So if they want, they just subscribe to our service and listen to whether there will be some alert. In the normal path, everything is good. The incentives is provided by our bounties. But when something went wrong, they will just receive the alert and trigger their own dispute path to ask their defensive validators to also validate the state, and then whatever schemes they already implemented.
Right, that makes sense. And just to reiterate and then drive the point home here, can you go over which components are on-chain, both L1, which pieces are on L2, and which pieces here are off-chain components being run?
Yeah, so here all these contracts are witness chain contracts. They're not deployed on L2. It's on yeah, and then all those. So these contracts are just on-chain contracts. And for the off-chain component, those watchtowers, they need to first, whenever they receive this like the event, when they find there's a new state asserted on chain, they will run their own computation, re-execute all the transactions off-chain. And they will also run L2 archive nodes to fetch these transactions to, so basically they need to first be an L2 nodes, and then they will run additional like watching responsibilities. Then they can post anything they have computed back to our contracts.
Right. And top right, when we have an EigenTower contract, that lives on an L2, right? Where does that live?
So this is basically the reward, how the reward will be distributed in this contract. It can be combined. So it's still the contract of witness chain. We can set the rules of how to distribute the rewards.
Got it. But just curious, where does that contract live?
It's on our mainnet.
Okay. And the delegation manager in the bottom right, as the EigenLayer contract, that's on Ethereum L1, right?
Yeah. Yes.
Okay. Awesome. Yeah. So moving on to, I think you were going to cover the transaction tracer, right?
Yeah. So before that, I will also briefly go over the other two workflow, the protocol and location. Yeah. These two have similarities. and we can just briefly see how they works, because we are going to launch them like in a couple of months. Maybe at that time we can do another series of that.
Yeah, let's do it.
Yeah, so so besides proof of diligence, the other two protocols we are actively build is the proof of backhaul for testing the bandwidth and the proof of location. But so behind their like motivation, they have different motivation and different physical attributes. But behind that, they share very similar framework for the like how to verify the on-chain, how to do the off-chain monitoring. So we will introduce them together. First, briefly, the proof of backhaul is akin to decentralized speed test. So the system will assess the internet connectivity and its capability to connect to internet of those DePIN nodes. So we also have those challengers. So we have basically there are two entities, prover and challenger. Prover are infrastructure nodes, and challengers are EigenLayer operators running those off-chain components. And the challengers will send small packets to the prover nodes, measuring their backhaul bandwidth based on the response rate, which is then will be aggregated to verify the proof. And there are three main stages: the challenge request, setup, and execution. So here for the execution, what we can see is, so we have this general challenge coordinator for different proof of X. And whenever they receive some request for this bandwidth, they will forward the request to both the prover and challenger. And here we will have some logic to implement how to select the set of challengers based on the request of the application and the provers. Then once they receive the notification, the off-chain parts, those challengers will send some signed packets. These are just a very small traffic because they will be aggregated before the backhaul link to like strong traffic which is enough to saturate the link of this they want to measure. And then once the prover receives enough packets, it will also compute the hash of those packets and send it back to the challengers. And these challengers, they will start a timer at the beginning of the challenge and stop it when they receive the response from the prover. So that will give them some measurement of the round trip time of the process, and they just report it to the coordinator. And we will have some aggregation algorithm like computing the median, so for robustness, something like this. But the logic is very simple, and the off-chain part is very lightweight. You can even run it like from your phone. And then for the proof of location, it's similar. So the architecture, we have a different diagram, but we can see the logic is very similar here. So the goal of proof of location is to determine the geolocation of DePIN nodes, but we still need to use internet measurements like the round trip time, then convert it to the distance, because distance is not directly measurable. So we still need to measure the time it takes for those internet packets to reach the prover nodes. And this method will further utilize some like principle of data transmission speed and internet geometry for accurate localization. And the basic method to determine the location is through those triangulation. But in DePIN scenarios, we further need to consider the adversarial behaviors, like what if the prover nodes use VPN, or they will collude to manipulate the measurements from some challengers. So even the distance, how to accurately measure the distance from internet delay. So these are all the problems we are going to solve. And to tackle these challenges, we propose this protocol, which consists two phases. So first is the calibration phase, where we will utilize some Byzantine-resistant data inferencing techniques to robustly translate the delay measurements into the actual distance. And the second phase is the actual measurement, and we will also combine those cryptography primitives to bound the uncertainty of the claimed location. But the like in terms of how to use it, it's similar. We have the coordinator, and you can send a request specifying who will be the prover and what is the claimed location, and then the challenger will the coordinator will select the challenger based on the claimed location. Select a set of like nearby servers. They will together send the data packets to the prover to estimate the time, then the distance, then together we'll figure out the uncertainty of your claimed location. Yeah, so then after going through the like basic principles of how these different protocols work and how we can utilize it, lastly, I would like to go over some use case of the proof of diligence watchtower networks and the transaction tracer and its APIs. So we're back to this. So basically, the transaction tracer is built to provide faster finality of those L2 transactions. So typically, if you're running some L2 node, you want to, for example, consider the scenario in a bridge for L2, L1, or like any two roll-up chains. If you want to know, you send a transaction on one chain, how can you monitor the states? Maybe we will use an RPC server to query the transaction. But there could be various issues such as the rate limiting or the server's downtime. So to address this potential problem and also further, we want to incorporate some faster finality rule and insurance scheme. We provide this method allowing users to trace a transaction through the responses from multiple watchtowers. So this process enables users to receive those multiple perspectives on the same transaction, and they can verify its finality based on the consensus among these watchtowers and further backed by their stakes. So it's particularly crucial for high-value transactions where users may want additional security, and they can also customize their security based on the total amount of stakes used to secure these watchtowers. So we offer this transaction tracer API for this purpose. And the users or applications can make this API request, which are handled by the coordinator. Then it forwards this request to several watchtowers, then aggregates this response to determine the consensus on the transaction state before returning the results to the users. Then here we provide the basic interface for, you can directly send API call here. And there are some like interface for handling the logging, the registry. But the main function is this trace. And the inputs are simple. You just need to provide the chain ID, the transaction hash, and a random request ID for tracking purpose. And the response will include the status. Yeah, the response will include the transaction status indicating whether it is finalized or whether it has been derived directly from an L1 block, and whether it's safe or unsafe. Users can review the details of this data from each responding watchtowers, and each of which will sign their submission to ensure the accountability.
Nice.
So the result also will highlight any consensus reached. So here, this is an example, so there's nothing here, but there, if we have, if they have any consensus reached among these watchtowers, it will show in this field, and allowing users to check the transaction status history and timing, like how much time you take from one stage to the other.
So
and
in this consensus field, when we say on status and it's empty, what does that mean exactly? And what are the possible values for what on status could be for the consensus field?
Yeah, so so this will depend on like what is the rule you request from the set of watchtowers you select. For example, you can ask for you will only accept the transaction if everyone says this is committed. Then at that sense, of course you need everyone to be like live, can get a valid response. but you will also get the maximum security out of it, because
Right.
if anyone is wrong, you will not accept it. And at least if someone want to mislead you on the result of some transaction, it needs to corrupt all the watchtowers.
Right.
So
Right.
you can definitely program your security need, have some trade-off in the liveness and security.
Is that part of the request parameters that get sent? Because I only saw 3, and I was wondering if you were to use it.
Yeah, at this stage, we just implement the simplest one that require everyone to respond. And I think later we can make it programmable to any other rules.
Makes sense. And going up a little bit for the second field in results where it says safety, what does unsafe imply here?
So the unsafe, so the status here reflects what is if we have a bunch of watchtowers, but only several of them respond, we will mark it as unsafe. And unless everyone is respond, or if you set up your security limit and the watchtowers reach this threshold, then it will become safe. And also, if the security is directly derived from L1 blocks, then it's safe.
So I'm guessing when you add more request parameters to specify the type of security you want, as a result of that, this safety field will give you a quick indicator of the result of that request being sent, as opposed to you having to parse a specific enum from the consensus field later down below, right?
Yes.
Okay, makes sense.
Yeah, so this will contain some details of the consensus.
Right. Yeah. No, this makes a lot of sense. Yeah.
Different.
And in terms of the chain ID, and I noticed, chain ID was one of the request parameters above. So what is the set of chains that are currently supported?
So currently, we've been monitoring the there are 2 chains. You can check the website here. So we have a base chain and optimistic chain watch, but these 2 are currently on the testnet because of some supporting thing, but we can quickly move it to the mainnet.
Got it. Okay. And so going back to the API and the transaction tracer, curious to get a sense of what some of the apps are that have indicated interest in using this API so far, and potentially down the road as well.
Yeah. So the very immediate use case we are this is developed for the bridges. So if you for any rollup chains between L1, L2, or 2 L2, if you want to just check the transaction submitted on the other chain, you can directly use this API. And also further, we will incorporate more complex mechanisms like insurance, because now to determine whether some rollup chain is finalized, you have a challenge period to finally confirm its finality. But with this programmable security behind it, we can get the faster finality immediately. And then once something's wrong, you will get insured. This is also some study I've mentioned before. So and not only the bridges, we can also implement light client to any chains. If they have a large, any proof of stake chain, if they have large set of validators, and light client don't want to just verify the signature of all of them, they can just subscribe to this kind of API to check the transaction status.
No, this makes a lot of sense for some of the immediate use cases that come to mind, and the impediments that we're seeing right now in industry, and where more security could definitely be used to offer, as you said, faster finality, or overall smoother experience for how you're relying on these products to work, whether it's bridges or otherwise, right? So exactly. moving beyond the immediate use cases a little bit, I'm curious to get your sense of, since this is your bread and butter, you've been thinking about this for years at this point. Now that you're seeing this sort of protocol come alive, what are some of the perhaps medium to longer term things that you see this design space unlocking? Maybe it's like, proof of diligence as a starter, but as you said, there are other protocols that you're working on with location and bandwidth and other proof protocols as well. So maybe it's like one of them specifically, or it's a combination of them. But zooming out a little bit, having these primitives, what are you personally excited to see?
Yeah, exactly. So we start working on this like from a very specific field, from those networking. So that's why like our first several protocols are around those network attributes. But then we realized that the DePIN world is very diverse, and there are many different assets. Each asset have different attributes, and like some of attributes, even like different different assets, they will share some common features, but even the same asset, it can have like very different aspects we want to measure. And this is the motivation of like establish the physical consensus layer on top of that. And then in terms of these proofs will definitely be the building blocks of this layer. So it's impossible for a single person to cover all the aspects. So we're thinking of to establish a forum which is similar to like ETH research for starting like discussing all this interesting problem on Ethereum for those digital consensus for different kind of security concerns. And here in the DePIN words, we want to also establish such a forum for different parties to think of and discuss, and also find the synergy between different sectors of the DePIN and how they can like, I also just mentioned some our existing partners, they're actively thinking of these interesting problems, like even for our existing protocol, like proof of backhaul, how to extend it to have a new implementation to support a higher bandwidth measurement. And for example, for some other devices we have not played with, like energies, our partner Daylight, they also propose their own proofs for that. And then further, there are lots of other opportunities. So we've been working on like with some AVSs, for example, OpenDB, they want to combine the proof of location with some storage. So not only you want to prove something is like some network device is in a location, but also there should be some file storage, something like attached to the location. So how to bond different attributes together, this is also not a trivial problem. So I think this will require a lot of innovation, a lot of interesting together to build this coordination layer.
Yeah, wow, that's super interesting. The having a proof that something is stored somewhere physically. If I read that, if that's what I heard correctly, right?
Yeah. Yes. So
Okay.
because location is it's an attribute, but if you want to someone is here, it's different from like some file is at this location.
Right. Yeah.
So even just for the location, there are a lot of interesting problems to think of, and we also have like all these different attributes for like energy device, for storage, for computing resources. So it will be great that people can contribute to the
100%. One of the things that I've been thinking about over the last several years as the problem of misinformation has been more, I guess, critical to think about, right? When you end up, this is much more of a consumer setting, but when you end up recording something, right? And that, whether it's a video, image, whatever, and that gets geotagged, right? You can have a signature on that asset being produced from your phone or whatnot, sure. But how do you actually go about proving that that location is where you said it is, right?
Yeah.
And if you're reporting some kind of news event or something, right? Like how do you trust that it's actually being reported from where it says it's being reported, right? So
yeah, exactly. This is a very interesting use case, and like especially for those journalism, how to prevent those fake news, fake image. happens to, if you want to record something, some event happen at the exact location. So we've been thought of this use case a bit, but I think the final answer might be some like combination of the protocols like proof of location, trusted hardware, because like in our current image, if you take it from your phone, from camera, they will have some metadata about the location, but this is can be added. It's editable. And one straightforward way is we can replace this one or add additional information of the proof of location here. It's a certificate for different nodes surrounding you. They can send the packet, send those packets to whether you are at that location at the time. But the problem is we still need to further bound the actual image to this kind of certificate. So this may need like additional layer of bounding technique. For example, trusted hardware, you need to prevent the images not sent from other server, and then before getting the timestamp or getting the signatures. So I would think this is a very interesting problem or applications to build, require both the DePIN side, those physical, the hardware manufacturer they're working on, and with the process they're building.
Yeah, no, I mean, that's the whole point of all this, right? You build one primitive, then you build another primitive, and you build a third primitive, and you put them all together, and next thing you know, you have this use case that wasn't previously possible to incorporate into how just information flow in the world happens, because information flow is like possibly like information science is like possibly the most important thing. So if you don't know how to direct it, how to rely on it, then you end up questioning a lot of things, a lot of digital products, a lot of how people end up consuming info, how society at large ends up essentially getting shaped as these things bubble up, right? So yeah, no, awesome to see these protocols actually going to production and being used, especially with sound research and theory behind them. It's amazing.
Yeah.
Cool. Well, if there's nothing else you want to go over for now, I think this is a good place to wrap it. Yeah. Any final remarks or anything you want to close off with?
Yeah, I think that's all I want to share today, and just feel free to contact us if you have any questions on.
Yeah, we will share the link to a bunch of stuff that you shared here. But in case people want to reach you, how should they do that?
So we have a Discord community for this open discussion, and like you can also, we have some like Telegram, any information if you want can follow us. And
yeah, so there's Twitter, there's Discord, there's the research forum that you're coming out with. So yeah, a lot of places to get in touch with the team, which will be linked as part of this post. So thanks so much for taking the time. Yeah, this was amazing and excited to see even more of this and the other proof protocols come out and people build on top of them. So yeah, thanks so much.
Thanks, Nima, for organizing this. Thank you.
Yeah, awesome.